Welcome to test review 3. In this test review, we are going over memory management, partitioning, paging, and page replacement. We will also be going over file management system commands. So to start off with file or memory management, what is partitioning? So we have our main memory block, and we need to allow programs to access parts of this memory block. So here are our processes' memory footprints. This is the size of memory they will take up. And we just put them into the main memory. And there's a few different ways we can put them in there. This is just one example. You can see in this example, we have a lot of unused space that we couldn't really use for anything else. So the first method we have is static equals sized. We have 3 equally sized memory partitions within main memory, and we'll just put each one of these processor footprints into this equally sized block of memory. And you can see here we have huge gaps where we're not going to be able to put anything else, and that's going to be a lot of wasted space. Then we have static unequal size. We kind of give rough estimates of, okay, here's a small block we can put a small process in. Here's a medium block we can put a mediumly sized process in. And then a large block we can put a large process in. But still we have wasted space, but much less so within this method. And then we have dynamic, which is the most expensive because you have to keep moving processes around to get them perfectly lined up in this way, but it'll waste the least amount of memory because you're just putting one process in, putting another process in right below that one. The issue becomes if this process finishes, you now have this empty space, and you have to move these 3 processes up to fill that space. All right, so we have next bit exercise. I'll pull up Paint for this one. So we have 6 processes. One has 600, one is 700 size, 1300 size, 2900 size, 300, and 500 size. And then we have 4 potential places we can put these processes. Let me see. Allocating in this order. That's 1. That's 3. That's 2. And process 6. So with next bit, we don't really care about the size of these boxes. We just care about which box each process will fit in. So the first one we're looking at is 600. We're currently looking at this box. This box is size of 1000, which will fit 600. So we can put that one there. Let me get my tool. Now part of that block is spent. And now we had a base address of 0, but since we have put something there, that base address has moved. 600, because that's the next available empty space. So it's now from 600 to 1000, and size has also shrunk by 600. So this is the 400 space that's left with a base address of 600. Now we will look at the next box and the next process we have to allocate, which is going to be of size 1300. This box has size of 700, so we can't put it there. So we're going to move on to the next one. And then again, it does fit because we have 1500. So we're going to put it there. Now we take the base address of this box and we add 1300 to it, which is going to be and we have to subtract 1300 from the size that was available. So we get size left of 200. Now we are looking at the next available box. And now we're trying to allocate process 2, which is a size of 700, which cannot fit in this box. So we go back up to the top. We have size 400, so 700 can't fit there. So we're going to go to the next box. Now we have 700, which is exactly the size we're looking for. So we can take up that entire space. Now that that space is filled, this one just kind of doesn't, we're done with this. That one doesn't exist anymore. Now we have to allocate process 6, which is going to be 500 in size. So we go down a box. That box has size of 200, so we can't fit 500 in there. We have 300 there, so we can't fit it there either. We go back up here, 400, can't fit it there. So there's nowhere to put this process 6. Any questions about that one?
Can you like repeat how to use the size again?
So with size, let's look at this example. We had base address 0 and size of 1000. We put a process that had size of 600 in it, so we subtracted 600 from 1000 to give us the size of 400.
Okay.
And 400 is just how much space is left within that page.
Okay, got it.
And then I can write out what the actual final should look like. So we'll have base address 600, size 100, and we'll have that one got deleted, so we're not, or that one's 100% full, so we're not keeping track of that one. Base address 4900, size 100, and then the last one didn't change. So base address 9200, size 300. That's our final list of memory. Now we have worst fit. So we are looking for the largest possible box that these memory addresses can fit inside of. Let me grab the order. So we have P4, 2, and then P6. So we'll start with P4, which is 2900, which cannot be fit anywhere. If we look at all these boxes are smaller than 2900, so we can't actually put that anywhere, which will be cannot be allocated. P2, which will be 700. So within worst fit, we are going to look at all of the boxes every single time we allocate something and look for the largest one. So we have 700. We're going to put that 700 in the 1500 box. So 1500 will just become, its address will be 3600 plus 700, which will be 300. And we will subtract 700 from 1500. So the size will become 800. Right. And then now we want to allocate process 6, which is 500. So now we have the options 1000, 700, 800, or 300. 1000 is the largest, so we're going to put 6 in that. Be about half. So this base address will become 0 plus 500, will be 500. Size will be 1000 minus 500, 500. So the final list will be base address 500, size 500. That one was unchanged. So base address 1500, size 700. And we have the new base address of 300, size 800, base address of 9200, size of 300. Any questions about that one?
Oh, just a quick question. So, what exactly is the white space like and red space is like exactly used for here? Or if it sense?
Like, what would be the practical use of this?
Anyway, yeah.
Worst, I couldn't see this ever being a good idea, honestly, but like, I don't have any industry experience, so I couldn't say whether like this is something companies actually use or not. But I mean, you can see here there's tons of wasted space where like you could have put this 500 in the 700 one, and then you'd have like 200 of empty space. But here we have 500 of empty space, and then let's say we wanted to allocate process 2 within this one, we couldn't.
Okay.
So I mean, at worst fit is a bad option, but it is an option.
Okay. And just confirm, like the red color like means it's filled, right?
Yes.
Okay.
Any other questions for allocation? All right. I'm going to save this. So we'll move on to other partitioning policies. We have best fit, which is similar to worst fit, where we are looping through all of the available boxes and finding the one that is closest to the space of the process we are currently trying to allocate. So if we have a process of 700 and there is a box that has 700 space, we're going to put it there. First fit is again just going to be the first box we come across that can accommodate that process. But it doesn't keep track of, or with next fit, we wouldn't go backwards in the list to see where we could put a process. Within first fit, we can do that. So if I recall correctly, you would start at the first box and go all the way down every time and see which box will fit that process next.
So
And
upon fitting a box, then you start at the beginning with the next one and look through the list.
yes.
Okay.
All right, and on to paging.
All right. So paging, well, in paging, you have a partition for both the main memory and processes, and you want to split them up into generally equal sized pieces, as you can see in that image there. Um, could you just click one more time, Chris? Yeah, there you go. So the process partitions, those little colored tables, or sorry, not the color tables. That we'll get to that later. But a page is a partition of a process, but the page frame is the partition of memory. So just that little distinction there. And then we want to allocate pages to the page frames. So just how you allocate processes to places in memory, you're going to do the same thing, but this with pages to page frames. And as you can see, we use a page table. So one page table per process, and that maps the pages to the page frames. On to translation. So in our we have logical addresses, and physical addresses. Your logical address is just the location of the desired data in the process, and the physical address is the location of the desired data in the memory. Now, we need to convert the page number that we get from the logical address to the frame number from the physical address, and we use that using the page map table. And both addresses have two parts to it, right? Logical address has a page number, the physical address has a frame number, but both addresses have an offset. The offset remains the same because the page size equals the page frame size. So let's go to some examples real quick. So we have, in this example, a main memory size of 512 kilobytes, so 2 to the 19th, a page frame size of 32 kilobytes, 2 to the 15th, and a logical address space of 512 kilobytes, 2 to the 19th. Now, we need to find how many physical page frames there are. So our little formula to find the physical page frames, if you could click once, Chris, is our physical main memory divided by the page frame size. So our physical main memory is 2 to the 19th, and our page frame size is 2 to the 15th. Now remember, when dividing exponents, right, you just need to subtract it. So you do 19 minus 5, and you'll get the answer, if you could click once again, Chris, 2 to the 4th. Are we all good on getting physical page frames? Okay. All right. So next is how many logical pages. That should be pages, my bad. So to find your logical pages, you use this formula instead. You use your logical address space, not the physical main memory, and then again divide it by the page frame size. So now we're doing, again, 2 to the 19th, because our main memory and our logical address space is the same size, divided by 2 to the 15th, so we should also get the same answer, 2 to the 4th. Yep. Any questions on logical, getting the logical pages? Okay. So now we're tasks with finding the logical page number, right? We're given the physical memory of 2 to the 22nd, a page frame size of 2 to the 15th, and a logical address space of 2 to the 19th. Now we have this logical address given to us, 0x5c32a, right? So our first step is we take that hexadecimal address and we convert it into binary, which will give us this wonderful number. Once we have that, we need to separate the page from the offset, right? And how do we know how many places we had to count? Starting from the right, as always. How do we know how many places we need to count for the offset? Does anyone know?
It'd be the logical address space divided by the page frame size.
That's for
Which is-
the page, right? Not the offset. How about the offset? The offset's the one in blue, not purple.
Would that just be like the page frame size?
Exactly, yeah. So the page frame size is 2 to the 15, so you just need to start counting out 15 bits, starting from the right. And so we get that whole blue section. That's our offset. And then how do we get our page? How do we tell that it's 4 bits? I think, Walter, you said it earlier.
Yeah, that's 2 to the 19th divided by 2 to the 15, which is 4.
Correct, right? So we get 2 to the 4th, which is 4 bits. So we count out 4 from the offset. And that leaves us with a leading 0 that we don't need, right? That's why you always have to start counting from the right. If you started from the left, you might have accidentally included that 0 and you would get a different number. So now that we have this binary number 1011, we can then convert that back into hexadecimal to get our page number. Which gives us 0xb. Any questions on that?
Okay, so you're just converting the page, right?
Yep, we're just getting the page number.
Okay, got you. 0xb. Got it.
Mhm. Okay, so now using that answer from before, 0xb, and the same logical address, 0x5c32a, what is the hexadecimal physical address? So the first thing we had to do, right, is find the corresponding frame and then convert that into binary, right? So if we look at our table on the left, we have 0xb and the corresponding number is 0x6. And then we convert that into binary, which will give us 0110. Now, after that, we need to combine this binary frame number with our offset from before, right? So that blue part that we separated from the page, from the earlier example, we take that, combine it with 0110. Once you have that binary number, you want to convert that into hexadecimal, and that will give us our physical address, 0x3432a. We all good on that?
Gotcha. So basically, to kind of like review it, we are taking the page number from the original address.
Yep.
We're converting the page itself into the frame, and
Mhm.
then so we got the 0xb. And once we converted it, and then once you got 0xb, you look at frame, then
Yep.
convert it to page in the chart. So 0x6. Then do that to binary, then add it to the original.
To the offset, yes.
Gotcha. Okie dokie. Cool.
All right. Any other questions on this one?
Are we gonna? There's some questions in like the practice that asks how many bits are needed to represent a valid or represent a physical page number or a logical page number.
Yep.
Um,
That will be on the. I have a little slide right next to
all right,
this one.
cool. I'll shut
We'll
up.
go over that in there. Okay. Any other questions on this example so far? All right. So, we still have the same physical memory size of 2 to the 22, page frame size of 2 to the 15th, and logical address space of 2 to the 19th. But the question asks, given the logical address 0x79686, what will be the logical page number issued by a process? And this is just for something you guys to work on your own. And once you get that answer, we'll talk about that first before moving on to that second question.
So, just to confirm, the
Yep.
page is like basically the basis of the logical address, right? In a way.
So we're using the logical address, right? The 79686. We're using that to get the logical page number that's inside this table on
Oh,
the left. And we're trying to find that page for the first question.
okay.
Yep. So give you all about, I don't know. I think a minute should be good. I should let everyone get there. All right, how are we doing, guys? Do we still need a bit more time for that first question? Okay. So let me just hear what you guys got for that first question. You can type it in the chat if you no worries.
Are we looking for like the logical page number?
Yep, that's the first question.
So that shouldn't that be 0xf?
Correct.
No.
Yep. Yep. So if you could click one time, Chris. Yeah, our answer is 0xf. Does anyone have any questions on why it's 0xf?
So you converted the logical address to binary and
Yep.
then use the far left minus the leading 0.
Yeah, and you should get just all ones for that page in the binary, right? You should have 4 ones, and that translates to 0xf.
Okay.
So remember, once you get that binary number after converting 79686, separate the offset, right? So count out 15 bits because our page frame size is 2 to 15. Count out 15 from the right, leave that 15 off, and then count out the next 4 to get the
Cool.
page
Appreciate it.
number. Okay. So now taking that 0xf, what is our hexadecimal physical address? So we're taking that 0xf, and then doing what we did earlier in that previous example. Give y'all say a minute or two.
For these problems, is it just easiest to do it on like a piece of paper?
Piece of paper would be definitely easier if you have trouble keeping track of everything in your head. Yeah.
Okay.
Yeah. Mhm. And if you don't have a piece of paper handy, you can always just open up like a notepad on your computer or something and just keep track of it there. Okay, it's been about 2 minutes now. Do we have any? Do we need more time, people, or we got some answers? I'll just take that as more time needed then. Give it all maybe 30 more seconds. Okay. So, anyone got any answers for this one?
So I was just like converting it the 0xf into the new hexadecimal.
Mm-hmm.
So when you're trying to get the hexadecimal physical address after you get the 0xf, what was the process again?
So, we take our page number, which is 0xf. We find the frame, right? 0xa.
Oh, okay. Oh, you're going the other way.
Yeah. Convert 0xa to binary. Add that to the offset.
Add it to the offset.
Mm-hmm. Do you guys want some more time just to work that out now that I gave some hints to that?
Gotcha. Isn't A like 10?
Yep.
Okay. Cool. So and as a general rule of thumb, can we just like copy like the first like 4 of the address and you just add it to like the last like bit or something? Or is there a simple way to like do it without writing everything out again?
I'm not exactly sure what you mean by that.
Because you said add the 0A
Yep.
Um
Offset.
to the offset. Yeah. Is there an easy way of doing it, or do you just like literally have to start from the beginning and just go right to left?
I mean, if you've kept the offset just written down somewhere, right, or typed out somewhere, it's possibly easier. All you
Okay.
had to do is convert 0xa to binary, and then just put that
Got it.
right in front of the.
Okay. Bet,
Yeah,
bet,
it's
bet.
not
Okay.
addition or anything. It's literally just putting it right in front of the.
Gotcha. So.
Yep.
0x. Wait a minute. So wouldn't it be just A79686?
No. So here, let's just go on to the answer real quick, and I'll explain where we're going from here. So our answer should be 51686, right? And essentially, once you converted a to decimal, right? Oh, not
Well-
decimal, sorry, binary.
Mm-hmm.
You have 101010, right?
Mhm.
Because that's what it is. And then you had to take your offset from before. So it should have been like 001 for the first three, and then 0110, 1000, 0110. That should have been your offset. If you combine 1010 to that offset, you'll get 51686.
Wait. You might repeat that again. Sorry.
Yeah, maybe it might be helpful. Chris, could you like open up a notepad
That'd be
really
great.
quick and just yeah. So you have your hexadecimal number 0x79686, right? I'll let Chris type that out.
Would you say that one more time?
Yeah, 79686. And you convert that to binary. It might be faster if you just convert it in your own calculator.
Yeah, let me throw it in a
Yeah.
converter. Someone taught Mike.
Realize the wizarding world of this era is fraught with dangers. Creatures corrupted by a magical force.
Walter, your mic's
powerful goblins.
Sorry.
Can't wait for that game though.
Yeah, I
definitely.
was like, oh man, I'm so hyped.
Yeah, so once you convert to binary, you get Chris, did you? Yes, yep. Nope, that's good. So yeah, so you get that binary number. Now we had to get the offset. So remember, the page frame size is 2 to the 15. Starting from the right, we had to count out 15 bits. So just go ahead and highlight 15 bits for me, Chris. Yep. So starting from that 001, that's your offset. And Chris, if you just copy that and like paste it just down below, or just like on separate lines to differentiate them.
So you would get the first 4 non-zero values, or
You just get. Are you talking about the page number?
yeah,
Yeah. So starting from where the offset left off, the first 4 bits, which would be those 4 ones. That's why you
Gotcha.
get 0xf.
got you. Cut it off from the
Yep.
offset. Okay.
And then once you have 0xf, you use the table, get 0xa, the corresponding frame. You convert 0xa to binary, and you get 1010. So just yep, 1010. That's 0xa, right? 10. And then all you do is you take that, and then you just put it right in front of your offset from earlier. So that 001 value, you put it there, and you should get your hexadecimal value.
Okay, wait. So
Do you
where's
need
this
to increase
011?
the text size, Chris?
Say again.
Do you think you could increase the text size?
Yeah,
I don't know
that'd
if
be
everyone
great.
could read that. Yeah. Cool. Yep.
Cool.
All right. So Walter, you were saying
Yeah, where's the 01111?
the 4 ones. That's your page number. Remember?
And you could disregard these leading
Yeah.
zeros.
Forget about the leading zero. Don't worry about
Yeah.
those. But yeah,
Oh,
so that
where's-
line 3, that's your 0xf, the page number.
And sorry, the spacing is habit of 3181.
It's fine. I feel that too.
Yeah, no, I did the spacing as well. I was just wondering like where that if you're just adding it, then where did all the ones go? Like all the ones, did you replace
You're
it?
replacing it, yeah.
Oh, that
Because the offset doesn't include those 4 ones. The 4 ones are the page number. Those don't get counted in the offset. The offset's everything after those 4 ones.
gotcha. So then that will give. You got one. Oh, so the 001. Do you mind adding the spaces again? Since like the one is like part of like the new one.
Yeah,
It wasn't there, but the
I
one
think the
was
space is
there.
there.
Yep.
There. There.
Okay.
Cool. Does that make sense to everyone else as well?
So we basically just like quickly
Uh,
converting, right, and not adding from each line.
Yeah. We're just converting and essentially just replacing the page number with the frame number.
Oh, okay.
So, because like your page number, right, was like it converted to hexadecimal was 0xf. We
Hmm.
replace that f with an a, which in binary is 1010, and that gives us the hexadecimal physical address, which is 51686 instead of 79686.
And the 3 and 4 like comes from the line 2, lines 3 and 4.
Yeah, so
from line
line 2 is the binary value of line 1. So line 1 is that hexadecimal value 79686.
Got.
Line 2 you convert it to binary. Line 3 you get the page number, right? So counting out that 15 bits for the offset, separating that from the 4 bits of the head. That 4 bits is those should be 4 ones, not 4.
got it.
Yeah. And then once you have those 4 ones, convert that to hex, you get 0xf. Check the corresponding frame number from that table on your left. 0xf corresponds to 0xa. Convert 0xa to binary, you get 1010, right? And you just replace that a page number from line 2 with 1010. That's how you get the value at line 4.
And like just to confirm, like where did like the 1111 came from?
That's the head, remember? So remember we're counting out the offset from the right, those 15 values. So
Okay.
Chris, you want to highlight? Yeah. So that's your offset right there, right? You start from the right, count out 15 bits. So your whole offset is 001, 0110, 1000, 0110. That's your offset. Then remember we did the logical address space divided by page frame size to get the page numbers, right? 2 to the 19 over 2 to 15.
Hmm.
You get 2 to the 4th, right? So we need 4 bits, because 2 to the 4th, that exponent is the number of bits, to get the header. That's where you get
Oh,
1,
okay.
1, 1, 1.
All right. I get.
Mhm.
Oh.
Good question, good question.
The spacing is a bit weird, but they're actually leading zeros here.
Huh.
And that's why it's really important you start counting from the right and not the left. Those leading zeros could trip you up. So make sure you count from the right. Do you guys want another example that we can all go over again, just in
Sure.
case? Or
Sure.
okay. Let's see. Let's make up one on the spot.
Uh,
Oh, Stone, did you have a
yeah. Can you like start with like 1001? Are they? Wait. No. Hold on. Never mind.
Make up some random hex number.
right?
I thought that was starting with line 2 sometimes.
Let's see. We could go, yeah, 6, 8, 7. Yeah, okay. So assume we have the number 67879, right? You want to convert to binary, right? You get this number. You take your page frame size. If you could move the window just a little bit down, Chris, so we can see the page frame size. Yeah. So you count out the offset based on the page frame size, right? 2 to the 15, count out 15 bits from the right. Yep. And then, and you get the leftovers, right? And can anyone tell me how many bits do we need for the head? How do we find that again?
Is that the one where you divide again?
Yep, that's the one.
So 219 divided by 2 to 15, which is 4.
Correct. So we need to count out 4 bits. Again, starting from the right. Okay. And that's our page number. Now we need to convert this binary value, 1100, to hexadecimal. Can anyone do that real quick for us?
Yeah, that'll be 12.
Which in hex would be
C.
correct. So we get 0xc as our page number. And we look at our table. What corresponds to 0xc? 0x5. Yep. Now, taking 0x5, we need to convert that back into binary, which would be, anyone want to give a shot at converting that? 0x5 to binary.
0101.
Yep. Correct. So we take our 0x5, convert to 0101. All right. Now, can anyone tell me what we need to do with this frame number to get our hexadecimal physical address? What do we do with it?
Replace.
Replace what?
You replace the front 4 of the from the left side, like the 1100 that you got 0xc. You
Yep.
replace those numbers with the 0x5.
Correct. So those numbers pass the offset, right? So what we initially pointed out was 1100, right? You replace that with 0101 and you'll get
Yep, that looks right.
Yep. And now we toss that into our hexadecimal conversion and we'll get 0x2f879. Did everyone understand how we got there? Any questions on that? Okay. Looks like we're good then. All right, Chris, you can move on to the next slide. So after our whole paging thing, we have demand or demand paging, right? We only need to keep parts of the process at one given time. We don't really need the entire thing all the time. So to do that, we can just keep a cache, which is really fast storage, right? And that just holds a little part of the pages from the process, or some of the pages, not all of them. Now, this allows multiple processes to be in memory, right? Since we're not using all the pages of a process, we can just keep little parts of it. We can have multiple processes. And each process only has part of its data in the cache, right? Remember, we're not taking the whole process, just parts of it. Now, when we're processing, we had to check if the data exists already. If it does exist, that's a hit, right? And we can grab the data from the cache. But if it doesn't exist, right, it's a page fault or it misses. And you had to load the data into the cache before you can use it. And nowadays, we also have the potential for virtual memory, so we can have even more pages than page frames, which is a good thing. But that's just kind of some extra tidbits. You don't really need to worry about that too much for this class. And so we need to find out, how do we know which pages to put into memory, right? When we're in demand paging. And so the first thing is you put the demanded pages into empty page frames, right? Because if it's empty, there's nothing already there. Just put stuff there, right? But the thing is, what if there are no available page frames, right? So now we had to choose which pages to evict or remove, and then replace that chosen page with the demanded page. Now, the question of which page should be evicted, that falls to the page replacement policies. And we have 3 of them that we go over. We have first in, first out, FIFO, second chance, and least recently used, or LRU. So our first thing is FIFO, first in, first out, right? So let's go over this example. We have a main memory with 2 page frames, right? And it's a bit smaller than the stuff you'll go over in the test, just because if we did like the full 4, it would just take a really long time for these examples. But there are some practice questions all the way at the end if you want to stick by or stick around after if you want to do that. You guys can try and practice on those. But for this example, we'll just do a smaller scaled down version. So we have a main memory with 2 pages, or 2 page frames, sorry. And this sequence of pages is requested by process. So we have 1, 5, 3, 7, 5, 3. Now we need to identify if the reference will cause a page hit or a page fault, and then to which frame will that reference be allocated to. So the first thing is we set up a little table. Right? So we have a page that has the 153573. We have our status column, and we have a page frame column. So the first thing we can do, right, we have 2 page frames, right? So we can automatically allocate our first 2 numbers, 1 and 5. And since there's nothing in our page frames, right, they're both false. So we can put FF. And since 1 came first, right, let's go to our first page frame, which is A. And 5 can go to our second page frame, which we'll call B. Everyone with me here? Any questions on this part? Okay. So now, in our sequence, we come up onto 3, right? Remember, there's only 2 page frames, so we don't have an empty page frame for it. So we had to replace one of our existing pages with 3. First in, first out, right? So the first in will be the first out, and the first in this time was page 1. So 3 is a fault, because 3 was not in any of the page frames. And then we replace it, we put it into page frame A, replacing 1, because 1 was there first, right? And we repeat this sequence with each new process. Anyone have any questions on that? I know it's not like a step-by-step thing, but it is FIFO, so it's relatively easy compared to the other things. Okay. So let's move on to second chance. So second chance, let's keep the same thing where we have 2 page frames, A and B, right? Same sequence of numbers, 153, 573. And so again, we can do the first 2, right? Because we have 2 pages. We can just go ahead and allocate the first 2. And of course, they're both false, right? Because there's nothing in the page frames at this point. So we have fault for 1 and 5, and then 1 will go to A since it came first, and 5 will go to B since it came second. And now we are requesting to put 3 somewhere in there. Of course, our 2 page frames are already full, so we had to decide which one to take out. So we look at our little queue, right? 1 came first, 5 came second. So the first thing that will get replaced, it will be 1. So 3 is a fault, right? Because 3 was not in any of the page frames. And replaces 1, which is at page frame A. Everyone good so far?
Yep.
All right, cool. Now we come up on our in the next thing in the process, next thing in the sequence is 5. Whoops, there's a little error in our little list on the side. Don't worry about that. But yeah, so 5, and it's going to be a hit, right? Because 5's already in our page frame. right? So it's a hit, and where was 5 located? It was located at B, so same page frame B. Now we got to do something to our queue, right? Because this is second chance. Now 5 has a second chance in case in case something needs to be replaced, right? So I just mark it with like a bold 5. You can mark it however you want. Just as long as you remember that that represents that it has a second chance. And a very important thing to remember about second chance is that they don't stack, right? So you can't have 2 second chances at once. You can only have one, right? So 5 now has a second chance, and we can move on to the next thing in our sequence. That next thing is 7, right? 7 does not exist in our page frames, so it's a false. And now we look at our queue to decide where we're going to allocate it. We check 5. 5 has a second chance, right? So 5 loses its second chanciness, and it just moves to the bottom of the queue. Click 1. Yep. So now 3 is at the top. Now we check 3. Does 3 have a second chance? No, right? It didn't have any. So we replace 3, which initially was at page frame A, with 7. Just click one more time, Chris. Yep.
So when it gets like a hit, when a number that's already in the queue gets a hit and it gets bolded, does it go to the back?
No. When it gets a hit, it stays in that place. Remember,
Oh.
second chance is just a variant of FIFO, right?
Okay.
So unless it's losing that second chance, it will stay in that same order.
Okay.
Good question though. All right. And now with this current queue, we go on to our next page, right? With 3. 3 again is a fault because 3 is not in our page frames. And the first thing in our queue that's getting replaced is 5, which is at page frame B. And that's what we end up with. Any questions on that? Okay. So now it's least recently used. So
Okay. One more thing.
Yep.
So the second chances don't move if they lose. So okay, you said that on the exam we won't have to do with more
so
than
wait,
2
hold on.
page frames.
Let me interrupt you real quick. If they lose the second chance, they move in the queue. If they gain a second chance, they don't move.
Oh, okay. If they lose, they go to the back.
Yep. Mhm.
Okay.
And what was that part you were saying at the very end of about the exam? Walter.
Sorry,
Yeah.
I'm called. What's up?
Yeah, you were saying something at the end of that about the exam. Was there something about the exam you had a
Oh
question?
yeah, you said that you want to do like a long one or something, like long because it takes so
Yeah.
much time.
So these little mini examples are scaled down versions of the stuff you'll see in the exam. The exam, I think, has the ones you'll see like on your practice quizzes, which
Gotcha.
is I
Okay,
think
for
4
sure.
frame sizes. We
Definitely.
have some of those at the very end if you want to stick around after all this. You
Definitely.
can attempt those, but
For sure.
yeah, for
Appreciate
these
it.
examples, it's a little scaled down so they take less time.
Definitely.
All right, so least recently used. Again, 2 page frames. Identify which one if they cause hits or faults and whatever's. So the first 2 just get allocated in, right? Fault, A, B. Easy done. And just keep track of your queue. So just click one more time, Chris. Yep. This is especially important in least recently used. Really keep track of that queue. Otherwise, you'll get pretty confused. Maybe not on this example since it's short, but definitely with longer ones. Yeah. So next thing is 3, right? Again, 3 doesn't exist in there, so it's a false. We look at our queue. What's the first thing that needs to be replaced? It's 1. So it goes to page frame A. Now 5 comes in again. So 5's a hit, right? Because 5's already in our queue. However, unlike in second chance, when we get a hit, the 5 doesn't stay in that same place in the queue. It moves to the back because it just got used, right? Least recently used. It's not the least recently used anymore. So now we go to our next request, which is 7. 7's a fault because it's not in there. We check our queue. What's the first thing that needs to get replaced? It's 3. So we replace that. And now we have our queue of 5, 7. Now the next request is 3, right? Again, it's a fault because we don't have 3 in our page frames. And we replace our 5, since that's the next one in the queue, with 3 to end up with this. Any questions? No? Okay, let me just leave you off with the. Remember that in second chance, it's a variant of first in, first out. So when you get a second chance, the number does not move to the back of your queue or whatever. It stays in that same order. It only goes to the back if that second chance gets used. That's different from least recently used, where if it gets a hit, it moves to the back. I hope you guys really remember that one, because I've seen people get mixed up on that on the exam. So just remember that again, second chance, it's a variant of FIFO, least recently used, something different.
So, just to confirm, for these like different examples, do they like use the page frame differently? Like, whenever like we try to like find like the hit or the fault?
Not that it uses it differently, it's just they'll have more. So instead of 2 page frames, they'll have like 3 or 4.
Oh, okay.
Yep. Any other questions? Okay. So next would be file management.
All right. Yeah, so with Linux, there's a couple of file management commands that you might need to use just when working on projects and stuff. That includes ls, which is list files in a directory, cd, which moves your directory, like your current working directory, mv. Sorry, further moving files and whatnot. Copy for copying files. RM for deleting stuff, removing files or directories and whatnot. Chmod, which changes permissions of a file or directory. That's something that you guys go over quite a bit. File determines the type of the file, and find is used to find files or directories in your system. Back to the permissions and stuff for the files and directories. There's 3 different types. You have owner, which is signified with U, group is G, and other is O. And you can assign various permissions to these groups and types. If you actually use LSL and then a file type, a file like a text file or a folder, you'll get an output that is something like that example there, where it has a group of 3 letters and dashes there, signifying which group has which permission. So in that example there, the owner would have read, write, and execute permission. So that's the RWX portion. The group would have read and write, which is the RW, and other would have read. And you can notice from the example there that if they don't have a permission, if that group doesn't have a permission, then there'll just be a blank dash there. All right, we can go ahead to a question here. So which of the following answers here can list all of the files in the current directory of type PDF? And you have some commands there on the left that you can look at that might help you out. All right, we have Walter with A or D. All right, Chris, if you want to click to the next slide, let's see the answer. So yeah, LS star PDF A is correct. What is the dash A again?
Dash A is for hidden files.
Oh, okay. So also you'll notice in answer D it has dash A, so including all the files, and then only just .pdf. So I'm not sure if that would be legal or not.
So the reason it's wrong is because that's list and not
Oh
ls.
yeah, toy.
I think you need the star before the .pdf for it to work too.
Yeah.
Yes. The star just makes sure it's everything selected. If you guys worked with databases yet, you'll use star for selecting everything in a database, and that essentially carries over in here. The star means for all PDFs.
Same thing with importing packages and libraries and stuff. All right, we can go ahead and move to question number 2. And so yeah, this is on the permissions for files. In this case, it's a file, not a directory or anything. And we're asking for which command would set the file owner to have read and write permissions, the group members to have execute permissions, and others to only have the read permission. So this is different from the previous example. This is using the chmod. All right, we got a few answers. We can want to move on here. Yep. So, yep, you guys got it. You're just setting the various users. What is it called? The yeah, for the owners, the group members, and others, you just set those individually there, and you predicate that with the file that you're trying to change. All right, so a question here: how would you view the contents of a file named answers.txt through the command line? All right, got an answer here. All right, so Chris, you can click for me. Yep, we got cat answers.txt. Cat is editing, so if you just do cat and then a text file, it'll open it up in your terminal and you can edit it and also view it.
And that's everything we have for you today. Do you guys have any questions, either related to the content that we just went over, or just general questions about the test? The floor is open.
Yeah, actually, I had a couple. So I was looking at the practice for the hexadecimal paging exercises, and one of the questions asked, "What's the logical page number in decimal?"
The logical page. That's just converting the so the page number say 0xf, right? You just convert that to decimal, and that's your answer. So 0xf in decimal will be 15, right? And that would be your answer.
Oh, okay, it's like the actual value.
Yep.
Okay.
Mm-hmm.
Then I had a few more, but I'm not sure if other people have questions.
All right. Anyone else have a question before Walter asks?
Yeah.
Yeah. Okay.
So, just to confirm one more time, for the let me just take a look. The page replacement, we have to look at the page, right, in order to solve the problem for both things, in order to determine if it's a hit or a fault.
So we had to look if the page itself is in one of the page frames that we've allocated. So in our example, right, we had page frames A and B, right?
Okay.
And if our value, say the number 9, if that wasn't in either page frame, then that would be a fault. But say 9 was already in page frame A, right? Then that would be a hit. So we had to look at what numbers we stored in each frame at that point.
Okay. Got it. Thanks.
Yep. Okay. Any other questions? Walter, I know you had a couple.
Yeah, my next question was so bits, just to confirm, it's what's left after you do the division between like the address and the page frame size.
No, so the bits are just the exponents of those values that you found. So say you were calculating the page number, right? The 2 to the 19 over 2 to the 15th, you get 2 to the 4.
Mm-hmm.
That 4, that exponent, that's
Gotcha.
the number of bits. So 4 bits.
Okay, and then another question was what do you do if there are empty spots in the page table and they use just like it's regular numbers? There's like a question that use like just numbers and it had like empty spots within the frame. I guess you just won't use it or something.
Yeah, so any of the empty spots, that just means they're not being used.
Gotcha.
I know which question you're talking about. Yeah, so again, if it's binary values, you just had to make sure you're converting to the right number system to use the
Okay.
table. In this case, the
Okay.
table in our example is hexadecimal, so we had to convert our values into hex and then find them on the table. Right.
Okay.
Good question though. Any other questions, guys?
The last question I had was if it's asked what are the maximum number of entries in the page table, is that just however many like spots that are not empty?
Uh, yeah, you're talking about that same question, right? The
Same
one with the
question, yeah.
yeah. It's just the ones that have been allocated to.
Okay.
Yep.
Okay.
hmm
Uh,
Any other questions, guys?
Yeah.
Oh, yeah, Stone.
So unlike the page reference examples, like this one, like the one like you're showing here, like has like the bits, and like the other one has like numbers, right? Uh, they're technically the same in a way, right? Or are they
Could
different?
you repeat that again?
Yeah, sure. Unlike the page practice question 3, like there was like numbers, like just like 10, 4, 1 under the page status. That's like a different type of page frame, right? Thing.
Let me see if I can just pull up that assignment. Which one are you looking at?
Replacement practice 3.
Placement practice 3. Oh, here we go. Page replacement practice 3. And yeah, so those that like 10, 4, 1, that's just a different numbers that are being requested. In our example, we had I think like 1, 5, 3, and 7. The actual values of those page numbers don't matter in the page replacement. It's just where they're being placed into, or which page frame they're placed into.
Okay.
hmm The values matter when you're doing paging, like this one, where you're getting the logical addresses and hexadecimal physical address. But with the on-demand paging, that's what you're talking about. The actual value of the pages don't really matter. Just
Oh,
the
okay.
just the order and where they're placed.
Got it.
Yep. Any other questions, guys? If not, we can move on to those extra practice for the on-demand paging. Oh, go back a bit. Yeah, there you go. All right, so you guys got this example over here, right? This time with 4 page frames, so not just A, B. Let's say A, B, C, and D. Get your little sequence of pages, and just go ahead and have at it for a bit. And let's see. How long do you think we should give him, Chris? Maybe like a couple minutes or so?
For this, a few minutes, yeah.
Yeah.
This can take some time.
Mm-hmm.
Two questions. Is this still being recorded? And how should we type our answers?
So as for the typing the answers, don't type it out, just keep it down somewhere and we'll show you the
Oh,
correct
okay,
answer.
cool.
You can just compare. As for is it still being recorded, Chris? I think the recording's still going on, right?
Yes.
Yeah.
All this will be recorded.
Oh, okay. Wasn't so sure if like the extra practice thing is gonna be recorded. So yeah.
Might as well, right? If people watching it wanna.
Okay.
Yep.
I messed up something with the recording, so I'll actually have to do a little bit of editing. But your professor should have it out by like tomorrow.
Okay, it's been a couple minutes. Do you guys still need a bit more time? Or have you gotten it down? I'll take that as you guys need a bit more time. All right. Everyone else good now, or
I'm good.
okay? Stone, Jake, Chris, how you guys doing so far? Almost done on that, or
Yeah, I'm good.
okay? Stone.
Uh, I'm just watching along right now.
Okay. Chris, how about you? Just watch along as well, or
This is my laptop.
oh, okay. In that case, go ahead and show off the answer, Chris. And I guess guys, just take a bit to compare answers, see if you got it right or not.
I ought to just use Zoom so I don't have to do that, but it works.
I mean, you can use the what's it called? The Windows game bar to record as well.
Well, no, so the thing is, I'm trying to, like, if you listen to the first recording, like, every time someone joined or sent a message, you hear ding, 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 ding. So I just use a non-host account to record.
I gotcha.
And Google doesn't provide a way just to mute the notification sounds.
Okay. Well, Walter, you're good. Jake, you all set? Any questions on that? Jake?
Oh yeah, I'm good.
Okay. All right. So let's just move on to what was the second chance will be next, right? Yeah. All right. Um, let's just say 5 minutes so we don't keep everyone waiting too long. Give you 5 minutes. After that, we'll just show the answer. And is 5 minutes too long? Nah. I think five should be
Yeah, I
good.
think that's a good amount of time.
Yeah. All right.
I'm good.
All right. We got about another minute left on that time. In case the other guys were just wondering.
Oh yeah, I'm good.
All right. Chris, you want to show the answers? Nice. And just let us know when you're done checking, Walter and Jake.
Sweet. All good.
All right. And Jake?
Yeah, I'm good.
Excellent.
Sweet.
And lastly, least recently used. Put another 5 minutes on the clock. Just tell us if you finish before that, though.
I'm good.
Cool. And Jake, you still need a bit more time? Jake, how you doing so far? Still need a bit more time?
No, I got it now.
Okay.